Hi, I'm Bernardo Clavijo from Artlam Institute in Norwich, UK. This introductory video shows how to use the CADCOMP tool to check the K-mer spectra of your genome assemblies. Many of the slides come from our de novo assembly training. So first, here are links to this video, my introduction post about K-mer counting, which I hope I will have time to make it into series at some point, and the CAD application note and supplementary material. There's a lot more information there, so if you're not familiar with K-mer counting, maybe you want to just go to the post first and read it before you watch the rest of the video. This is a typical K-mer spectra, so errors to the left, genome content to the right. There's a lot more information to be read here. I'm not going to discuss choosing K or anything like that. There's material in the links for that. Just know that CAD by default uses K equals 27, and it uses Jellyfish internally to do the K-mer counting. Remember that to produce a clean K-mer spectra, you will need a high base pair accuracy, which basically means you will use CAD most of the times with Illumina arrays. Let's start with the genome that's perfectly unique, and if you're sequencing this, every K-mer in the genome appears in the genome just once. If we sequence with no errors 10 times a K-mer coverage, we will expect to see most K-mers around 5 to 15 times, following a distribution center at 10 times like this one. So what if we have some content that appears twice? We will expect to see those K-mers following a distribution center around 20 times, like this. Obviously, if some content appears thrice, we will expect to see those K-mers following a distribution center around 30 times. So if we take this boring old K-mer spectra, which by the way is from a yeast genome, so this is a real sequencing, quite old actually, and we take its reference genome, we can partition this. We can separate the distributions of the K-mers that appear 1, 2, 3, 4 times in the reference. So what we will get is something like this. You can see here the K-mers that are unique 2 times, 3 times, 4 times. Also you can see an absence in the reference distributions that is mostly sequencing errors, and you can see they appear obviously very few times in the reads. So this is where it gets interesting. You can actually do the same with the genome assembly rather than a reference. So basically you take how many times a K-mer is sampled in the reads, how many times it is included in the assembly, and you compare those two. And since you're creating the assembly from the reads spectrum should be very well partitioned. So that is exactly what CADCOMP does. And this is what we call the spectra copy number plot produced by CADCOMP. It plots the spectra from the reads for every copy number in the assembly. We show this as a stack histogram, so it looks like the whole spectrum of the reads painted in colors by copy number in the assembly. Note the red bar at frequency 0. These are K-mers that were not in the reads but are in the assembly, so most likely errors, or if rather than an assembly you use the reference genome, those could be real SNPs of your sequenced data versus that reference genome, or obviously errors in the reference. So the easiest way to check an assembly with the spectra copy number plot is to start by checking that all content which should be included is there. So in this example, the assembly on the right is losing a lot of content, the black distribution representing absent content that's 0 times in the assembly. So a perfect spectra copy number is a necessary condition for an assembly to be correct. So you can have a perfect spectra copy number and your assembly can either be correct or you can still have some other kind of errors or biases. But if you have an incorrect spectra copy number, then your assembly cannot be correct. Basically you don't have the right content in there, or you don't have it in the right number of times. So Anyway, do remember that most assemblies are incorrect. It's just a matter of knowing how so and if they are still useful for your research purpose. If we have a look at the example on the CAT application note, that's a heterozygous genome. So you can see there's two peaks. Obviously the first one, the lower frequency one, corresponds to heterozygous gamers. That's gamers that appear just in one of the two haplotypes. And the second one will be homozygous gamers. That's gamers that appear in both of the haplotypes. Obviously, there will be some cases where that's not 100% true, but the bulk of those distributions will be from those gamers. What you have is two different assemblies, and the assembly on the left is representing a haplotype and a little bit more, if you want. You can see that it's recovering most of the heterozygous content, but not all of it. There's a little bit of black in that distribution, and also there is a bit of duplication on the homozygous content, whilst the assembly on the right is not duplicating the homozygous content almost at all, and it seems like it's discarding not quite half, but a large proportion of the gamers that are heterozygous. So if you have a good read through that paper, you'll see an example of how you can actually work to assess heterozygous assemblies. There's a lot of information in the supplementary material for that, and this is one of the main uses that we give CAT-comp. So finally, here are two good usage examples involving long reads. Please note that in both cases, CAT-comp is actually performed versus the Illumina reads in these hybrid datasets. So on the left-hand side, on the Trio-Canoe paper, there's a lot of spectra copy number plots. This one is from an Arabidopsis cross. Now, what you can see is the content recovery here is quite good, and the partitioning is quite good. You can see that everything is pretty much recovered. The first peak appears once in the assembly, the one in red color. The second, the homozygous peak, appears basically twice, and so on and so forth. So that's a very nice result indeed. What you can also see is that there's a little bit of a red bar at zero frequency on the reads. That means there's some content that appears just once in the assemblies that was not present in the Illumina reads. Now, most of the times in this case, those are going to be small one base pair errors or insertion deletions on the assembly, where the consensus accuracy is not quite perfect, but this is a really nice result. Now in the figure from the right, from the hybrid PacBio Illumina with assembly, we're showing only the missing content distributions, so the part that's normally represented by the black distribution, from different assemblies. So this helps show which assemblies are recovering more content, but also there is an interesting addition here. So the lowest line, it's a distribution that has been computed by basically putting all of the assemblies together and then checking which gamers from the original Illumina reads were not included in the assembly at all. So those are gamers content that no combination of sequencing technologies and assembly algorithms shown in that paper recover from that dataset. So these are two really nice papers that do take into account content recovery, so if you have not read them, you really should. So that's been a very high level introduction to CAT-comp. Here are the links again, where you can find a bit more detail on all of these topics. We're also always happy to answer CAT related questions, so just write to our Erlang Institute emails or contact me on Twitter. Thank you.